Okay, let's unpack this. Forget everything you might expect from a sorting algorithm that, compares one element to another. Today, we are diving into something that works fundamentally differently. We're talking about counting sort.
Right. And our guide for this exploration is Hello Algo. We're pulling insights specifically from their section explaining sorting algorithms, which lays out counting sort with impressive clarity.
It's a wild departure because instead of comparisons, counting sort, well, it sorts by counting. It actually uses the values of the numbers.
Exactly. It's a non-comparison sort, which immediately sets it apart and gives it some, well, unique properties and, importantly, limitations.
So our mission today is to really go deep into this unique algorithm. We want you to truly understand its clever core idea, see the steps involved, appreciate its power when used correctly, and know precisely where its boundaries lie. By the end, you'll know counting sort inside and out enough to explain it yourself, hopefully.
What's fascinating here is just how simple the core idea is, really. At its heart, counting sort works by figuring out how many times each distinct element shows up in your input array.
It almost sounds too straightforward, doesn't it? Just count the occurrences. And the source makes it clear this is typically for arrays of integers.
Yes, and the most natural fit is non-negative integers, because it relies on using the integer value itself as an index. The brilliant part is that when you store the count for, say, the number 5 at index 5 in an auxiliary array, well, the indices of that array are already ordered, right? 0, 1, 2, and so on. So your count array inherently organizes the distribution of your numbers in a sorted way.
Okay, I see. It's sort of like creating a frequency map or maybe a histogram where the bins are the numbers themselves. The height of the bin tells you the count, and the position of the bin tells you the value. If you read the bins left to right, you're basically seeing the numbers in order. How does that core idea translate into, like, a working algorithm? The source starts with a simple implementation.
Right, let's imagine we have an array of non-negative integers. Let's call it nums.
Okay, what's the very first thing you need to do?
For this simple version, you first have to find the maximum value present in that nums array. We can call that m,
Why find the maximum first? What's that for?
because it tells you how big the auxiliary array needs to be, the one we use for counting. If the largest number is m, our counting array, which we'll call counter, needs to have a slot for every possible integer value from 0 all the way up to m. So its size has to be m plus 1.
Got it. So, step 2. Create that counter array size m plus 1, probably initialize with all zeros. And its only job is to store counts. Counter value tells us how many times value was in the original nums array.
Exactly. So the next part of step 2 is traversing the original nums array just once. For each number, let's say num, you simply go to the counter array at index num and you bump the count up by 1. You're just tallying up occurrences. It's very straightforward.
But simple enough. Process the input, build the count. Okay, once you've done that, the counter array holds the sorted distribution. So the final step in the simple version must be reconstructing the sorted array using those counts.
Precisely. Because the indices of the counter array are inherently sorted 0, 1, 2, up to m, you can just iterate through the counter array from index 0 upwards.
Ah, right. Index 0 in counter tells you how many zeros were in the input. Index 1 tells you how many ones, and so on. Makes sense.
Correct. So you iterate, let's say, with num going from 0 up to m. For each num, you check the value in counter num. If, for example, counter num is 4, you know the number num appeared 4 times. You then just write the value num into the original nums array, sequentially, 4 times. You do this for each num from 0 to m, writing it out as many times as its count indicates.
And just like that, the original nums array gets overwritten with the sorted sequence of values. That flow seems pretty clear, but the source is quick to point out a pretty significant limitation of this simple approach.
Yes, this version, it effectively sorts the values, but it doesn't give you back the original items associated with those values. That's the key issue. If your input was, say, an array of complex objects like customer records you wanted to sort by age, well, this simple counting sort would just give you a sorted list of the ages. You lose the actual customer records. You lose the payload, the original data you probably cared about sorting in the first place.
That's a critical distinction. You sort the numbers, but not necessarily the things represented by the numbers. Okay. Before we tackle that limitation, the source makes a neat connection to another algorithm, bucket sort.
Yeah, they mentioned you can think of counting sort as a specific form of bucket sort.
How does that link work? What's the connection there?
Well, in bucket sort, you usually divide your range of possible values into several buckets, right? Then you distribute elements into those buckets. With counting sort, the idea is pretty similar, but each possible integer value from 0 to m effectively becomes its own tiny bucket. The counting process is essentially like placing elements into these individual value-specific buckets.
Okay, so it's like bucket sort, but with incredibly fine granularity, a separate bucket for every single possible value. That's a cool way to visualize it. Now, about that limitation, losing the original items, and also the simple version isn't stable, right? If you have duplicate numbers, their original relative order isn't guaranteed.
Correct. Stability is often important.
So the source introduces a more complete implementation to handle these issues.
Right. The complete version addresses exactly that. How do you sort the original data, like the objects, and ensure that elements with the same value keep their original relative order in the sorted output? That's stability.
This is where the algorithm gets, well, significantly more clever and, frankly, more powerful. The simple version had 3 steps. The complete version adds a crucial intermediate step, transforming the counter array.
Exactly. This new step 3 is calculating what's called the prefix sum of the counter array.
Prefix sum. That sounds a bit technical. How does that work, and what does it actually tell us in this context?
Okay, think of the prefix sum at index I. It's just the running total of all counts up to and including index I. You compute this by iterating through the counter array. For each element counter I, you update it to be the sum of itself and the previous element counter 1. After you do this, counter num no longer stores the simple count of num. Instead, it now stores the total number of elements in the original array that are less than or equal to num.
Okay, let me see if I get that. So if counter 5 becomes 12 after this prefix sum step, it means there were 12 numbers in the original array that were 5 or less.
Precisely.
And if, say, counter 4 was 8 before, meaning 8 numbers were 4 or less, now counter 5 being 12 tells us there are 12 total numbers up to and including 5.
Exactly right. And here's the crucial insight, the real aha moment the source points out. The value counter num after this prefix sum calculation, if you subtract 1 from it, that gives you the exact index where the last occurrence of the number num should be placed in the final sorted result array. It tells you precisely where the items need to go.
Wow. Okay, so the raw count told us how many of each number, but the prefix sum transforms that into telling us the target index for the end of where each number's block belongs in the sorted output. That's quite clever index manipulation. And this prefix sum information is key for step 4, which is completely different from the simple version of step 3, right?
Yes, step 4 is where you actually construct the final sorted output array. First, you create a new result array. Let's call it res, same size as your original nums array. Then, and this is critical, you traverse the original nums array, but this time you do it in reverse order, from the end back to the beginning. This reverse traversal is absolutely key for getting stability.
Okay, walking backwards through the original nums. For each element num we encounter, what do we do with it then?
You use that prefix sum information you calculated in step 3. You look at the current value of counter num. Remember, counter num 1 gives you the correct final index for the last instance of num that should appear. So you take the current element num you're looking at, or, importantly, the original object it represents if you're sorting objects, and you place it into the res array at index counter num 1.
Right, so if counter num is, say, 7 after the prefix sum, meaning the last num should end up at index 6 in the sorted array, you put the current element at index 6 in res.
Exactly. And immediately after placing the element, you decrement counter num by 1. This is vital. Why? Because you're processing the original array in reverse. You encounter the rightmost, latest occurring instances of any duplicate number first. By using counter num 1 as the index and then immediately decrementing counter num, you're essentially assigning positions in the sorted res array from right to left for identical elements. The element you saw latest in the original array gets placed at a later index in the result, which preserves their original relative order.
Ah, that clicks. That makes perfect sense for stability. When you hit the next instance of that same number as you continue going left in the original nums array, counter num has already been decremented. So you place that element at the index before the one you just used. You're filling in the spots for duplicates from right to left in the sorted array based on their original right to left order. Clever.
Precisely. This reverse pass, combined with the prefix sum giving the final position of the last element and then decrementing the count, ensures stability. If element A appeared before element B in the original array and they have the same value, A will still appear before B in the sorted res array. Guaranteed.
Okay. Once that reverse traversal is complete, your res array holds the stable, sorted result.
That's right. And the final touch is often just copying the contents of res back into the original nums array if you need to modify it in place, or just returning res.
Okay, so that complete version is definitely more involved, the prefix sum, the reverse traversal, the new result array. but it buys you the ability to sort the original items and it ensures stability. That's a huge upgrade. Now, let's talk performance. What are the characteristics of counting sort? Time complexity.
Yeah, so when we look at efficiency, counting sort has a time complexity of O(n) plus m. Big O of n plus m.
O(n) plus m. Okay, unpack that. Where do the n and the m come from?
Sure. N is the number of elements in your input array, nums, and m is essentially the range of the input values. Specifically, if we're dealing with non-negative integers starting from 0, m is the maximum value. You have to do things proportional to n, like traversing the input array to count initially and traversing it again in reverse for the stable version. And you also do things proportional to m, like creating and initializing the counter array and calculating the prefix sum on it. So both n and m contribute.
Got it. So it's linear time with respect to both the number of items and the range of their values. The source also mentions it's a non-adaptive sort. What does that mean?
Right. That just means whether your input array is already almost sorted or completely random or sorted in reverse. Counting sort will perform roughly the same sequence of steps and take about the same amount of time. Its execution time isn't really sensitive to the initial sortedness of the input, unlike, say, some versions of quicksort or bubble sort.
O(n) plus m sounds quite good, especially compared to typical comparison sorts like quicksort or merge sort, which are usually O(n) log n. When would O(n) plus m be clearly better?
This is where the relationship between n and m is absolutely key. If the number of elements n is much, much larger than the range of values m, think n is way bigger than m, then that m term becomes relatively small, almost insignificant compared to n. So the complexity effectively approaches O(n), just linear time based on the input size. And a linear time sort is incredibly fast, asymptotically faster than O(n) log n. So in those specific scenarios, counting sort is a real powerhouse.
Okay, so large data set, small range of values, boom, super fast. What about the space it uses?
Space. The space complexity for the complete stable implementation is also O(n) plus m.
Okay, why is space also tied to both n and m?
Well, you need space for the counter array, right? And its size is m plus 1. That's the OM part. And for the complete stable version that handles original objects, you need that separate result array to build the sorted output. That res array has size n. So that's the ON part. Add them together, ON plus m.
Okay, so it's definitely not an in-place sort. It requires potentially significant additional memory, proportional to both the input size and the range of values.
Correct. It makes a very clear trade-off.
Yeah.
You get potential speed, but you pay for it with extra space. No free lunch here.
We touched on some stability, and the complete implementation is stable. Just to really solidify that, could you quickly recap why that reverse traversal guarantees stability again?
Sure. The stability comes directly from using the prefix sums to know the final sorted position for the last occurrence of any given value, and then filling the result array res by iterating through the original array nums in reverse order. When you process nums from right to left, you see the rightmost instances of duplicate values first. You place these into res at the highest available index for that value, determined by counterim 1. Then you decrement countertem. So when you encounter an earlier instance of that same value for the left in nums, the target index and counter has already been reduced, ensuring those earlier instances are placed at earlier indices in res. This strictly maintains their original relative order.
That makes total sense. Processing the original from right to left while assigning positions from right to left ensures that whatever was further right originally ends up further right in the sorted outpoint among its equals. Got it.
Exactly. It's quite an elegant use of the prefix sum index combined with the traversal direction.
So we have this powerful, potentially linear time sort. It's stable, it can sort original items, but it requires ON plus M space. What are the big limitations that keep it from being a general purpose sort like merge sort or quick sort? The source is quite specific here.
Yeah, the most significant limitation, the biggest hurdle, is its dependence on the data being fundamentally mappable to non-negative integers.
Right. What if you have negative numbers? Can you even use it?
You can adapt it, as the source mentions.
Hmm?
You need to find the minimum value, shift all the numbers up by adding the absolute value of the minimum to make them all non-negative. Then you sort using counting sort on those shifted values, and finally shift them all back down by subtracting that same offset. But this adds complexity, and it also changes the range in them you need to consider. It becomes the difference between the max and min values.
Okay. Doable, but adds steps. What about other data types, like strings or floating point numbers, or maybe even complex objects that don't have an obvious integer mapping?
For those, counting sort generally isn't directly applicable. not unless you can find a way to map them reliably to non-negative integers in a way that actually preserves their relative order according to your sorting criterion. For instance, you could maybe sort strings by their length using counting sort on the lengths. But then you lose the ability to sort them alphabetically, right? You need that value to integer mapping to respect the sorting order you actually want.
Okay, so you really need that clear order-preserving conversion to non-negative integers. That's a big constraint. And the other major limitation seems tied directly to that M term in the complexity, the range.
Absolutely. Counting sort shines when n is large and m is relatively small. Its performance, and especially its space usage, really degrades if m becomes very large.
So what happens if you have a data set where the numbers are within a massive range, even if there aren't that many actual numbers, like, say, sorting just 100 items where the values range up to 1 billion?
Yeah, that's the killer scenario for counting sort. If m is extremely large, like 1 billion, then the space complexity OM becomes the deal breaker. Trying to create a counter array with 1 billion elements, it's simply not feasible in terms of memory for most systems, even if you only have 100 input numbers and 100. You'd likely run out of memory long before you finish sorting.
Right, the memory cost would be astronomical. And even if space somehow weren't an issue, if n is much smaller than m, the time complexity O(n plus m gets dominated by the OM term, right?
Exactly. If you're sorting, say, 10 items in 10 with values up to 10,000 and mid 1,000, the time taken would be proportional to roughly 10,000. A comparison sort like merge sort would take something like O10 log 10, which is drastically less. So when n is much smaller than m, counting sort isn't just space inefficient. It can actually be significantly slower than standard O(n log n algorithms.
That really locks in its niche then. It's definitely not the algorithm you just grab for any old sorting task. It's highly specialized for specific data types and distributions.
Right. It's a powerful tool, definitely one of the fastest non-comparison sorts available when it fits. But it's only applicable when your data meets its constraints. Essentially non-negative integers, or easily mappable to them, with a range m that's not excessively large relative to the number elements n. Understanding this trade-off, this specific applicability, is really key to mastering sorting algorithms in general.
So wrapping up this deep dive into counting sort, drawing from our source, Hello Algo, we've seen its unique, pretty simple core idea of sorting by counting occurrences. We saw how the complete implementation brings in those clever prefix sums and the crucial reverse traversal to handle original items and guarantee stability. And we've broken down its O(n plus m time and space characteristics.
And importantly, we also highlighted its strict requirements regarding data type and value range, really emphasizing that it's a specialized tool, not a universal hammer for all sorting nails.
It's a great example of how different algorithms are designed for different problems, different situations. There's rarely a single best sort. It always seems to depend on your data and what you need to achieve.
Yeah. And this brings us to a final thought for you, the listener, to consider. Looking at the very distinct trade-offs, counting sort makes, trading space proportional to the value range for potentially blazing linear time speed, but only for specific kinds of data. How does the fundamental nature of the data you are dealing with in any given programming task fundamentally dictate which algorithm you should even consider? It goes beyond just looking at the big O notation on a cheat sheet, doesn't it? It's about understanding the algorithm's underlying assumptions and how well they actually mesh with the real-world data you have in front of you.